morning, everybody. Should we start? Is everything okay? Okay. Okay, I'm going to be speaking on detection and evasion of web application attacks. Now, a little bit of housekeeping before I start. Some of the slides on your printed material might be quite different from what's showing up on screen because I was working on this till the very last minute. So the updated slides will be available on the Black Hat website for you. The other issue is that I'm going to give you a little bit of a background about how this all came about being. We were approached by a company which wanted a way in which we could detect whether their clients or their systems were being attacked using SQL injection or cross-site scripting attacks. So the first idea that we had was, hey, why don't you go and look into your web server's logs? You might see some information out there which might give you indications of whether an attack is taking place or not. Unfortunately, that fell through because in your web server's logs, you do not get post data. You only get data that is sent as part of a GET HTTP request. So then the idea was that wherever this information might be, it might be coming as the traffic is flowing into your network. So if we could do a regular expression match and see if the regular expressions match with what is typically sent as part of a SQL injection or a cross-site scripting attack. The couple of tools that we use, since the idea was not to develop a whole new solution, but to see what exists and see if it can be tweaked into doing web app detection, we use two tools. We basically used the Snort intrusion detection system, and we used mod security, which is an additional module that comes with Apache web server. So what we're going to be seeing out here is mainly Snort intrusion detection system being used with regular expressions to detect web application attacks. And then we're going to see where Snort will actually fail to detect. Snort essentially, as you would know, is a signature-based mechanism. Primarily, it's signature-based. So there are certain attacks where signature-based detection mechanisms would absolutely fail. So we're going to look at that, and then we're going to look at some possible solutions where we might still be able to catch these attacks taking place. Now, a couple of things from what I need from your end is, when I'm showing you a particular signature and I'm saying that this is the attack and this is the signature which will detect that attack, you could just raise your hand and holler and say, hey, that signature is crap. I have an attack that can actually evade that signature. So if you give me input like that, then that helps us write better signatures within Snort. Because the problem out here is that the team that has written these signatures is the team that has actually launched those attacks. So it's pretty trivial to write a signature for an attack that you're going to launch. You know what kind of traffic you're going to send. So you're going to write that kind of signature which will catch that kind of an attack. The idea out here is to make it as generic as possible to try and catch attacks which other people might send in, which we may not have been able to imagine when we wrote those signatures. Okay? So we're looking at two types of broad level detection techniques, what I call as static detection and then what I call as dynamic detection. Static detection is typically what happens post-event. You've already been hacked or you suspect that somebody used a web application vulnerability to break into your website, and what you want to do now is go into your web server's logs or your application logs and figure out what went wrong. Since log analysis is something that is covered quite a lot in depth in various websites, we're not going to go too much in depth and see what log analysis mechanisms you're supposed to use. What we're going to concentrate on is dynamic detection. Okay. Here I divided into two parts, signature-based and anomaly-based. And then the idea is going to be to take a typical set of web application attacks. What I've done out here is I've taken the OWASP top 10. On the OWASP website, there is a top 10 list of vulnerabilities in web applications. So the idea out here is to see those 10 different types of attacks which exploit those vulnerabilities, and then see how we can actually catch those attacks taking place. Okay, right now as the situation exists, a lot of companies are putting mission critical data on their web applications. This is stuff that we all know about. And you are allowing people to come in through port 80. So the attacks have all moved up the layers and moved on to the web application layer. And a lot of discussion of web application security really focuses on how do you prevent web application attacks by doing better by following better coding practices, or how do you actually attack a web application? So there's a lot of stuff out there on breaking web applications and on secure coding. What's not out there a lot is how do you detect that an attack is taking place at this point of time. So a lot of solutions and products are coming into their own just about now. You have a bunch of products out there that do application level intrusion detection system. Again, since the idea out here is not to focus on commercial solutions, we'll not be looking at a lot of those in depth. Unless, of course, those guys are willing to pay me for this. Existing detection methods are being tested before customers really accept this as a standard. Like network-based intrusion detection systems, although Gartner might disagree, are standardized solutions right now. So application-level IDS solutions will become standardized going into the future. Although this is going to be primarily a textual-based solution, I thought I'd put in a nice graphical picture about where this solution will actually fit in. Now, your IDS could be, normally your network-based IDS could be debated. It could be in front of the firewall or behind the firewall. But out here, you want your application-level IDS to be as close as possible to your web application. So in the case of mod security with Apache, it actually runs on the web server itself, or secure IS, or URL scan. These are solutions that are going to run on the web server as filtering mechanisms themselves. So you want your application-level IDS to be as close as possible to the web server. Okay. Now, I've done this sort of a rough classification. Again, I'm not sure if this classification is standard or not. I broadly classify them into static and dynamic, and then dynamic is further classified into anomaly-based and signature-based. Now, if you're planning to conduct an effective and a thorough web application investigation, there are certain fields of information that you need. Some of these are common across any network-based intrusion. You need the IP address from where the traffic is coming. You need the timestamp. But you also need the HTTP method that was used. And you need the uniform resource indicator that was requested by the user or the attacker, as the case might be. However, what you also need and what you will not find in your web server's logs is the entire set of HTTP data. The attack could be sent as part of HTTP headers, or it could be sent as part of a cookie, or it could be sent as part of post data. So essentially what we are looking at is the entire set of traffic coming from an end user or an attacker to your particular website. Like we discussed, static techniques will typically happen after the event has already occurred. So you're going to look at parsing the log files, and the aim is forensics investigation, whereas in dynamic detection techniques, the idea out here is to trigger an alarm when the attack is actually taking place. So this is more real time as and when the attack is happening. In static detection techniques, you're going to typically look at the web server logs. If you're using a 3-tier architecture, you'd probably look at your application server logs as well. If your application has been written in a way in which it creates an audit trail, for example, I think there is another presentation on detecting web application attacks by coding your web application differently. So if in case your web application is coded where it creates in-depth audit trail, then you would want to go through the application audit logs also. The operating system logs would not be very effective information if you're trying to do a forensics on a web application attack that has occurred. However, in all of these pieces of information, what's missing is post data. Most of the information that gets sent from a browser in the HTML input fields is going to be sent as post data. That's missing from your web server's logs, from your application's logs. HTTP headers are also only partially represented. You do not have the entire set of HTTP headers that could get sent from a client's machine. And cookie or referrer data might also be used as input for malicious traffic. Again, this would not necessarily get shown on all the web servers. For example, let's look at an IS web server log entry. IS allows various options to be turned on what kind of information you want to get logged by IS. So if you choose all the options available, the maximum entry that you get is something that looks like this. Now in this, if I told you that this is a SQL injection attack, you would say there's no way that we can determine if it's a SQL injection attack or not. But actually it is, because this is exactly what we're going to do right now. We're going to use this particular web page, SQL inject 2.html, and inject SQL injection traffic into that. But there is no way that you can look at the web server logs and figure out if a SQL injection attack is taking place. So where are the areas that a static detection will fail to detect an attack? If the attack is against a web server where somebody is trying to overflow a buffer within some HTTP headers that are not there in the web server's logs, that fails. If it's a SQL injection or cross-site scripting or a parameter manipulation attack in hidden fields, that fails as well. Forced browsing. Forced browsing is an attack where an attacker will try to access a sensitive area without going through previous authentication. So let's say he tries to access a page called orders.php without going through a previous page called login.php, which would have authenticated him to allow him to access that page. So that's forced browsing. Now, if you wanted to determine forced browsing, it would be pretty tedious to do because you'd have to go through your web server's logs. You'd have to see a particular access to orders.php. Then you'd have to trace back and see whether there was a successful login on login.php or not, which is not very easy to do just looking at your web server's logs. So that's an area that's going to be difficult to detect using static detection. But some attacks are pretty trivial to detect using static detection. For example, the first stage of an attack would be an attack against the web server using automated tools, open source such as Nikto or Nessus, or any of the commercial tools available. These would show up very easily in a web server's logs. Okay, there would be ton loads of entries, and we'll see these. In fact, even your Snort IDS will trigger alarms all over the place when you use these automated attack tools. HTML hidden field attacks. HTML hidden field attacks are where developers place certain fields as hidden HTML fields and expect that this information will traverse back onto their web server as it is. They do not take into consideration sometimes that it's very trivial for an attacker to use a proxy such as Achilles or Paros proxy to modify this information as it's passing back to the web server. So if an attacker tried to manipulate this kind of information, it would be trivial for him to do that, and it would be difficult for us to detect that because it would not get shown up if it's post data. If it's get data, it would get shown up in your web server's logs. Another attack that is typically launched is either an authentication brute forcing or a session ID brute forcing attack. This would get shown up only partially in your web server's logs. You'd see ton loads of access to a page such as orders.php, but you may not actually see the session ID that's being enumerated across the entire web application. That brings us to what's really the core of the entire presentation, which is dynamic detection techniques. Now, dynamic detection techniques, you could either use an application level firewall or deep inspection firewall. They're trying to tweak that to detect customized web application attacks as well. You could use solutions that have their core focus only on application security. So there are commercial solutions that do detection only of application level attacks. Or what we're going to try and attempt here is to take something like Snort and try and stretch it and see if it can detect web application level attacks. The advantages that you have with dynamic detection is that you get the entire set of HTTP headers, you get data, post data, you get cookie data, you get all the information that you would need to carry out an effective investigation. This is a slide a rough comparison table that I drew up between signature-based and anomaly-based. Signature-based is easier to implement. Anomaly-based is more difficult to implement. You'd need slightly more complicated algorithms for anomaly-based. Signature-based, you could take something like Snort and tweak it up. Again, it's cheaper and a do-it-yourself solution. So if you're doing a cost-benefit and you figure out that maybe it's not justified to buy a commercial-level anomaly-based application IDS, you might go in for something like Snort. If your signatures are too generic, you would get a lot of false positives. For example, we're going to look at a SQL injection signature which is very generic, which would trigger all over the place. So even for genuine traffic, you would see that signature being alerted. Anomaly-based theoretically should have less false positives, but it would have false negatives as well. An attacker might be really smart and evade the learning mechanism that an anomaly-based IDS goes through. Signature-based traditionally has been used more for detecting web server attacks rather than for detecting attacks against the web application. However, if you actually go through the Snort rule set, you will realize that Snort has more than 850 signatures out of almost 2,000, which are only for web server attacks. Some of these are for web applications. A large majority of these are for attacks against, let's say, the IS web server or the Apache web server. In fact, the signatures for detecting cross-site scripting will not even trigger for a standard cross-site scripting attack. One of the products that's going to really help you if you're doing a lower cost solution is mod security, especially if you're using Apache as your web server. Mod security supports what are called as Perl compatible regular expressions. So if you're a Unix administrator, regular expressions is standard stuff for you. So you can use regular expressions within mod security directives, which are similar to Apache directives, and figure out if an attack is taking place or not based on a pattern match. The thing with mod security is that you can go right in depth. You can say that on this particular Perl or PHP page, I want this particular field to have only this kind of information. Or you can say that apart from this particular field on this particular page, on any other field, I do not want this kind of thing. So you can do pretty fine-grained checks using mod security. However, mod security will still fail to do what standard signature-based detection fails to do. It will not be able to detect an authentication brute forcing. It will not be able to detect a session ID brute forcing. If somebody is crawling through your website, mod security does not have directives to protect you from that as well, or to alert you for that. And if somebody does HTML hidden field manipulation, again, that would not get detected. Also, mod security, the author or the developer of mod security has provided a Perl script which converts this existing snort rule set into mod security directives. So you could use that to have one solution for your Apache web server. On Windows, if you're using IIS, you typically want to go with something like URL scan in case you don't want commercial products. Unfortunately, URL scan at this point of time does not support regular expressions. So let's look at the attacks one by one. The first attack that an attacker is going to use is he's going to try and break the web server. Okay. This is typically done using standard attack tools that are available, such as Nessus or Nikto. These tools have IDS evasion techniques, but you will see that even the IDS evasion techniques will still get triggered by snort. So we're going to look at a small demo where I'm going to trigger off Nikto on a particular website. So let's look at that. This is where all your alerts from snort will come. I have not installed. Let me explain what the setup really is. This laptop is going to be the attack machine, and there's another laptop out here which has the web server and the database server set up. Okay, so this is going to be the target for us. The intrusion detection system is running on this machine. It could be running on this machine as well. Okay. So what we're going to do is we're going to use Nikto to attack the target. And in this case, what I'm going to ask it to do is to check for all attacks, which is generic. Usually Nikto will see the web server banner and then configure its attack range only for that web server. I'm also going to trigger off snort and launch this. At this stage, you will see that there are a lot of alerts that will start cropping up out here. Okay, as you can see, if we go right to the end, there are 3,500 lines of alerts that will come, and these alerts will continue to come, so we're going to clear this up. And this is something that I'm going to have to do often because I'm going to tweak the rules of snort, so I'm going to have to restart snort over and over again. Now what we're going to do is, whoa. See, now that's Murphy's law, something has to go wrong, and okay. Now, I always thought I should actually have done this on Linux. Okay, now start Nikto back up again, and Nikto gives you IDS evasion techniques, it gives you 9 types of IDS evasion techniques, going from using case insensitivity to using double encoding, URL encoding, Unicode encoding. So what we're going to do is we're going to take the entire set of evasion techniques and throw it at the web server and shoot up snort again. And you will see that the alerts do come. They're far less than the alerts that you saw in a standard Nikto attack. Okay, that's one. Second, most of the alerts that you will see are called double decoding attacks, because in this type of an evasion attack, he's encoding the first URL encoding and then Unicode encoding the characters. So you're going to look at most of the alerts as double decoding attacks. We'll come back to this a little later because snort will take a while to actually start alerting on this. The next stage that an attack, the other thing that I wanted to point out is for most of these attacks in the brackets I've put numbers such as A10, A1, A2. These actually correspond to the OWASP top 10 list of vulnerabilities. So if you want to correspond with that, that's the number you go with. The next attack would be where he tries to download the entire website. This is website crawling. The idea, of course, is to figure out the logic with which the web application has been built, HTML commands, so on and so forth. Again, there is no signature that you can write for this. This is an anomaly of the behavior. Okay, it's not an anomaly of the protocol. So what's happening out here is that you have a single IP address connecting to all the possible links within your web server, okay, within your web application. And for those of you who might have attended Saumal's lecture yesterday, where he spoke about defeating crawling tools, you will realize that the key difference is where a human being will take a definite amount of time of clicking between links, a tool will do it much faster. So one of the ideas we had was that it might be possible to write a snort preprocessor for this. Snort preprocessors are pieces of code that will try and detect attacks with signatures typically cannot. So you have preprocessors for port scans, you have a preprocessor for TCP fragmentation attacks, and you have one for HTML encoding attacks. So the idea could be that it might just be possible to write a snort preprocessor for this. The problem though is that this might be stretching out snort as an idea a little too far, in the sense that in a practical implementation, in a production environment, packets might start to drop. Okay. So I'm not sure if this would work or not. In this particular situation, what would work ideally is anomaly-based detection, because this is a clear-cut anomaly from a clear-cut variance from what is normally accepted traffic. The next attack we're going to look at is a cross-site scripting attack. As is commonly known, a cross-site scripting attack is more against the end user rather than the website. And the typical snort signatures that exist for cross-site scripting attacks, I've highlighted what snort tries to pick out, which is the script tag, and in the second attack, in the second signature, is trying to pick up the image source tag. Both common ways of exploiting a cross-site scripting vulnerability. However, there are numerous ways in which these signatures can easily be evaded. So what you're really looking at is just looking at the opening HTML tag and the closing HTML tag. Okay. So if you're looking out for that, you're always going to catch any and every type of cross-site scripting attack, plus you might end up catching a lot of other things as well. Okay. So that's the problem that we're going to see. Okay, you can see that snort has spewed out some alerts, and as you can see, most of them are double decoding attacks, but not as many as you saw with the default Nikto run. Now the problem is that we're running this with one attack machine and one target machine. In a production environment, you would have snort triggering off a whole bunch of alarms. Okay, so finding out something like 10 alerts related to somebody attacking using Nikto would be very difficult to do that. So we're going to shut this off and close. Okay, now for the cross-site scripting attack, what we've done is build a very rudimentary search page. This is a standard location where an attacker will try and figure out if you're vulnerable to cross-site scripting or not. The idea is, of course, that whatever input you're putting in has to come out as output. Can you see at the back what's being typed out? So what you might try to do is launch a standard alert. And if the site is vulnerable, you'll see this popping up. Of course, this is only proof of concept. So a simple snort signature for this might look something of this sort. In this case, what I've done is I've commented out most of the other snort rule sets. So what we have out here is this first signature, which says this checks for attacks which contain the HTML tags. So let me explain what this does. If you're familiar with the snort rule bases, I'm not going to get into those details. What I'm only going to talk about is PCRE. The PCRE keyword tells snort that what follows is a Perl compatible regular expression. So all that we're going to do is write regular expressions for this. In this case, what we're looking at is %3c, which is the URL encoded value of the opening HTML tag. Then we're looking at one or more non-new line characters and then a closing HTML tag. So when we have this sort of a rule in place, what you will see is that a standard attempt such as this will get easily flagged off. And if an attacker is on your website, the first thing that he's going to do is typically do something like this. Or he might do it a little less over the radar. He might go under the radar and say, put a bold tag or an underline tag, okay? But what you're always going to see is the tags coming in. So let's see if the rule triggered or not. And here you can see that there are 3 alerts that you got for the cross-site scripting attempt. So this is a very rudimentary regular expression that you could write. The problem with this is that if you have a web application where you're allowing users to input HTML tags, say you have a blog or you have users, posting on news groups, if your web application supports that kind of functionality, then these alerts would trigger off even for that. So the idea out here would be to actually put this as part of mod security and put an exclamation mark in the mod security directive, which would say that this signature applies to all the pages inside my web application except the page which accepts HTML tags. So you could do that with mod security. That's not possible with Snort. You can't do that fine-grained level of checks with Snort. So this would trigger off for almost any traffic that contains opening tags and closing tags. Regular expressions, by the way, also work with EI's secure IS. The idea out here is not to push EI, so we are not going to demo secure IS a whole lot. But if you have IS, then what you want to go with is that solution. Microsoft, of course, has a free tool called URL Scan, which does only keyword matching at this point of time. They, of course, tell me that they might be building a regular expression functionality in it, but I'm not sure when that will be out. So this is the signature that we looked at for cross-site scripting. And like I said, this will catch almost any remote attempt to attack cross-site scripting. It will give you false positives. The other kind of a vulnerability that exists in websites is malicious redirection. Sometimes websites have this functionality where they'll redirect you either to another location within the web application, or they'll redirect you to a partner website. So this can be used by a malicious attacker to redirect another user of that website to a malicious website. So for example, you could do something like this. You could take the IP address of your own website, you could convert it into octal or hex, and then convert it further into URL encoded values. So what you would see is in the last line, redirect.php target is equal to, now that string actually corresponds to 192.168.0.1, which is completely obfuscated. So the effect of such an attack is again the same as a cross-site scripting attack. Okay, you're sending a user to a website which he didn't intend to go to. Now it's not going to be easy to write a signature for this because the range of sites that you could be sent to is infinite. So what we are looking at is actually writing a white list of sites where a user should be redirected to and then blocking out everything else. This is again not possible with Snort. You can't do that with Snort. What you can do with mod security is you can say that this string, these are the list of accepted strings, and anything other than that is malicious. And again, this is something that is very easily caught with anomaly-based detection, because during the learning phase of anomaly-based detection, the product would actually learn which are the websites that users are typically redirected to. So any variance from that would get flagged off. Yes? With Snort, are you saying? With Snort, you want to alert yeah, you could do that. You're right, you could do that. But another possible solution might be mod security. You could do that with mod. Basically, you're attempting to create a white list, so you're saying anything other than that is, that's right. The next attack, like I said, is forced browsing. Again, this is something that's difficult to do with signature-based detection, but would be much easier with an anomaly-based solution. Now the attack that created a slight bit of controversy, we actually wrote an article about this on Security Focus, and guys from a company called Imperva came along and said, hey, these are the attacks that would actually evade all of those signatures, which is a good thing because it allowed us to write those signatures better. So initially this talk was titled Detection of Web Application Attacks. After that paper came out, I had to modify this and say Detection and Evasion of Web Application Attacks. So what we're going to look at is some standard SQL injection attacks being launched against a web application, certain signatures within Snort which will detect that, and then certain techniques to evade those detection mechanisms. Now, again, I've created a very rudimentary SQL injection page. The only difference between this and what you would see on a lot of other websites is that you can actually see what's being typed on the password, and the text area, it's a text area instead of a text input because you're going to type in some stuff out here. So a standard attack might be to feed in a username password, and if that username password exists, the idea is to put a single quote to close that, a semicolon and a double dash to end that. Then whatever comes after here is ignored. If a user called test actually exists on that particular database, you would be authenticated through. Now, in this particular attack, the attack is successful because of these SQL meta characters. So what you want to look out for is the single quote, the semicolon, and the double dash. Now, the first idea might be to write a signature for this, which looks something like this. Okay, this is the rule for SQL injection, which will catch all attacks. And what we're looking at here is, for the single quote or its URL encoded value, a double dash, a semicolon, or a hash sign. These are again all SQL meta characters. The problem with this you will find is that this is too generic a rule. As soon as you put this in place in a production environment, this rule will fire all over the place. So it might be easy to show this in a test environment where we have one target machine and one attack machine, but it does not typically work in production environments. It will give you too many false positives. Okay. Let's try that one more time. Okay, this is deja vu. We were once with a company and we were trying to prove that signature-based detection works. And we're sitting there with these signatures and we're saying the Snort rule will fire just about now. It's just going to fire, and it never fired. But this did fire this morning. So let's give it a few more shots. Sure oh sure, we have to uncomment it first. Okay, we're going to come back to that a little later on and hope that it fires a little later. Whoa, it did. So you get Snort basically buffers the attack, so the alerts will not get printed immediately to alert.ids. So you can see that it's triggered for that very trivial attack against a site that's vulnerable. Now, typically, once an attacker is trying to determine if the site is vulnerable or not, the next attempt might be a standard Boolean string, which is the very famous 1 or 1 equal to 1. In this case, since it's a string, since the information is going back into a varchar and not a numeric value, I'm going to have to manipulate using these single quotes. So again, a standard signature for this looks something like this. And what I'm going to do is I'm going to comment this signature back because that's what's going to fire first. And this is what that signature looks like. Out here, what we're doing is we're looking at first for the single quote or its URL encoded value. Then we're looking for the letter O and then the letter R. Okay. The idea is that if you try and write a too specific a signature for 1 or 1 equal to 1, you might find that it actually does get evaded because it's pretty trivial to do that. So again, when we're trying to, the other problem with this is going to be that we're essentially looking out for the letters O and R. Now this could be as part of standard HTTP traffic that gets sent to your web server. For example, if you have order ID is equal to OR123, this might get triggered. So you have a problem with this. So again, this is too specific a signature, and it might yield, it's too generic a signature, and might yield false positives. However, what will happen is eventually the attacker will realize that you are vulnerable to SQL injection. And that is the stage at which he's going to try and input certain SQL statements such as insert, update, delete, select, or union. Okay, so the initial attempt might be to just look for these particular values. So I'm going to enable that signature to look out for the keywords insert, update, delete, select, or union. The idea out here is, of course, to close this particular query, and assuming I have figured out the name of the table at the back end, I would try and insert a new user out there. Of course, close that query and comment everything out that comes after that. It gives me an authentication failure, which is fine because I'm not trying to authenticate. What I'm trying to do is to execute a query at the back end database. So here you can see that this particular signature has been fired on twice because of that attempt. Now, one of the evasion techniques that works very simply with this is simply to inject a C-style comment out here. So between ints and ERT, you can actually insert a comment out here. So what this does is, it still executes the same thing, okay? But you don't get the alert right now because you don't have the keyword insert occurring anymore. So your alerts don't trigger. So then the idea would be to actually watch out for C-style comments occurring, which is this particular signature, which tests for / **** and *** with anything in between that. So in this case, again, we have a Perl compatible regular expression which is looking out for the // escape the / and escape the asterisk. So now you can see that the SQL evasion attacks do get, the alerts do get triggered off. The other thing might be to look out for other keywords which are specific to the particular database being used. For example, Microsoft SQL Server allows you to execute extended stored procedures and stored procedures. So what you could do is you could look out for the keyword exec followed by one or more white spaces and then either an S or an X followed by a P. So this is what would be used typically to execute a backend extended stored procedure or a stored procedure. So you could look out for that as well. So we've covered this. What's really happening out here is we've seen these regular expressions being triggered off. This one is for SQL meta characters. Like we discussed, this leads to a lot of false positives. Sometimes it would trigger off even for genuine input. We've seen that these are problems that occur even when you're trying to do input validation. And again, with mod security, you could make it really fine-grained to work for a specific field on a specific page. Boolean SQL injection, the idea was, of course, to make sure that the backend query always results in a value true, which could be done in a variety of ways. So what you actually only want to look out for is the keywords single quote followed by an OR. Some of the other keywords we said, which we discussed, were important to check out for these. These are the evasion techniques. You could do URL encoding. Again, Snort has a preprocessor to deal with that. White spaces, you could put your signatures with one or more or zero or more white spaces, as the case might be. If SQL comments are being used to evade, you could use signatures to detect for that as well. Buffer overflows are not common against web applications as such. Buffer overflows yield much better results against web servers. So they are not always launched against a web application. However, you can sometimes get interesting results when you try and feed in a large amount of data to a particular field, which enters into a function. For example, in this case, you can see that it's not just a mistake in the handling of the large buffer, but there's also another mistake, which is the error information is being disclosed to the end user. So one of the signatures that might work for this is to look out for the query string will typically contain information of the type name equal to value. So what you're looking for is the is equal to sign followed by a very large string and followed by an and sign, which closes that particular name equal to value pair. However, this is a pretty lousy signature because it won't work all the time. We've seen that in production. Now this is where anomaly-based works really well, because anomaly-based, one of the parameters that you're taking into account during the learning phase is the expected length of the input parameter. So any variance from that will be immediately flagged off by an anomaly-based intrusion detection system. Command execution, again, Snort has a whole bunch of signatures to check out for Unix as well as Windows command execution. So that's pretty standard stuff. You can write a signature-based detection for that. However, Snort signatures can sometimes misfire. For example, if somebody tries an LS attack, and LS could be as part of normal input also. Okay, so you have a problem with that. The null byte poison attack is another type of attack which is pretty simple, trivial to write a signature for. All you're looking out for is %00, which is the null byte character. So it's pretty trivial to write a signature for that as well. Again, some other meta characters that might be used to execute commands at the back end. Now, where are the areas that signature-based detection will actually fail to work? Like we said, one of the attacks that is pretty standard is an HTML hidden field manipulation attack. Now, this is something which it's almost impossible to write a signature for. For example, if you're an e-commerce website selling, maybe thousands of goods, it's very difficult to write a signature which says that for this particular good, I expect only this value to come in. So, a standard attack that works against this is where you take an amount field and, of course, manipulate it. This is pretty old hat. I mean, you would be pretty lucky to find these kind of vulnerabilities on web apps nowadays, but they still pop up all the time. So this is something where you can't write a signature. For example, if I change the value 879 to something like 8 or 7 or 9, it would be very difficult to write a signature for this. Another generic type of an attack is called as an invalid input, where the web application is expecting certain numbers and we feed in alphabets. This is what could happen. This is again a real life example where we fed in the letters AA where a number was expected. So in this case, you can see that it's not only given the Java exception, but you also come to know about the backend Oracle application server and the version that it's being used. Again, it's pretty difficult to write a Snort signature for this. You could write a mod security directive. Yes. You could. That's one of the slides that we cover. For example, if you're doing authentication brute forcing, you're going to get an authentication failed output message. So you could write a Snort signature for that. But if you work with intrusion detection systems in production environments, you'll see that those kind of errors pop up a lot. But you could write a signature which does outgoing protection also. So that's a valid input. So coming actually to the point that I was making, which is authentication and authorization brute force attacks. Again, what you would see in your web server logs is something like getorder.php, and you would not see the order ID is equal to the value if it's post data. You would not see that in your web server's logs. All you would see is multiple accesses to the page getorder.php. So this is something that, again, it's difficult to write a Snort signature for, or do signature-based detection of this. So you would not see the actual order ID being visible in the web service logs. One of the ideas we had was to write some sort of a rule-based correlation which says that if I see this particular alert once and if I see it 10 more times in the next 1 minute, then that's an authentication brute force happening. Because in any production environment, there are ton loads of failed authentication messages that you will get, And a large majority of these will be genuine attempts. Users will actually be making genuine mistakes in supplying usernames, passwords. So what you want to really see is a malicious attempt, and the difference between a genuine attempt and a malicious attempt will be repetitiveness. So if you could write a rule-based correlation engine which basically says that if there is an authentication failure once, and if it happens a multiple number of times, then I want to flag that off. Now again, the idea that you gave, you could actually look for an outgoing authentication failed error message, but you would be flooded with those in a normal environment. Again, one of the ideas that we had was whether it's possible or not to write a SNOT preprocessor for this. This is something that we would be exploring in the coming few weeks. Anomaly-based detection is based on the assumption that you can actually define normal traffic. With any, whether it's a network-based IDS which works based on anomaly-based, or it's any other application-level IDS, it will go through two phases. One is the learning phase and one is the detection phase. In the learning phase, what we are typically going to be looking at is the input length, which fields will have what kind of input lengths, any variance from that will be flagged off, character distribution or parameter string structure. Here you could use finite state automata or language theory, and that's what typically most of the products use. You could also look at whether parameters are absent or present during normal traffic, because an attacker will typically, if it's a normal user, the parameters will always appear in the same order and they will always be present, or they'll not be present. It will be standard traffic that you'll see. If it's an attacker, the traffic might actually differ. Some parameters might occur, might not occur, or their order might change. So an anomaly-based engine is going to basically look at these kind of parameters. Also, what is important, there are some anomaly-based engines that will actually do the learning phase based on your previous web server's logs. Now that's not good enough because you're missing out on a lot of critical data. So a good anomaly-based detection solution should actually look at real live traffic rather than at the web server's logs during the learning phase. Currently, of course, there are only commercial products that dominate this field. Just to be comprehensive, I've included a slide which does mention some of these. Again, I have personally not evaluated any of these, so I cannot vouch for which one is good and which is not good, or whether any of them are good. Some of the key points, any questions before I conclude? Yeah. Because a lot of the critical information would not be there in the web server's logs. You would not have HTTP header information. You would not have post information. This is the kind of information that you would have when you're analyzing the entire set of traffic as it's flowing across the network. Web server's logs would be not containing as much information. The performance trade-offs would be better evaluated between signature-based and anomaly-based. So that's where you would want. And if you actually observe, most of the commercial anomaly-based products actually do load balancing as well. So a lot of them try to counteract the performance hit that will occur because of this kind of intrusion detection that's taking place. With SNOT, you would have the regular trade-off which happens with any other signature-based detection mechanism. So it's the same. So as we've seen, for a large majority of the attackers, the run-of-the-mill attacks would actually get caught using signature-based attacks. So you could use that as a first line of defense. But eventually you'll realize that if you have a really mission-critical application running, then you want a commercial application-level IDS being used. And maybe the best solution, in fact, most of the commercial solutions, I suppose, actually use a combination of signature-based and anomaly-based to detect application-level attacks at this point of time. And finally, like most of the other speakers, talk about, it's essentially all about the money. So it's really what kind of information are you trying to protect, how important is it to you, and then you do a cost benefit of whether a signature based is good enough or you want to purchase anomaly based. These are some references you might want to go through. Our article on security focus, the SQL signatures evasion article by Mookhey, mod security homepage, and one of the better papers on anomaly detection, which was released sometime last year. Any questions? Okay, thank you.